In this module, we will learn the total probability rule and the Bayes rule. To begin with, we'll recall the relation between the conditional probability and the joint probability of two events A and B. We know that the probability of A given B is equal to the joint probability of A and B upon the probability of B, where the probability of B must not be equal to 0. We can similarly write the other conditional probability B given A equal to the probability of B intersection A upon PA, where PA is not equal to 0, but B intersection A can be written as A intersection B because intersection is commutative. So we have these two relations. One implies that the joint probability of A and B is given by probability of A given B into probability of B, whereas 2 implies that the joint probability of A and B is given by probability of B given A into probability of A. But because these two terms denote the same thing, they must be equal, and therefore we can write that probability of A given B into probability of B is equal to probability of B given A into probability of A, which gives probability of A given B equal to probability of B given A into probability of A upon probability of B. This result is an important result and is known as the Bayes rule. This result is known as the Bayes rule, or sometimes also called the Bayes theorem. It's called the Bayes rule or Bayes theorem. It has 4 terms in it. The expression has 4 terms in it. PA is known as the prior probability. PA given B is called the posterior probability, and PB given A is called the likelihood. We'll note all this down later on. To understand this, let us consider a digital communication system in which A denotes the transmitted symbol and B denotes the received symbol. Let A denote the transmitted symbol and B denotes the received symbol. It is usually known that if A is transmitted, what is the probability of receiving B? And the communication problem is to find out the probability of transmitting A if B has been received. So in that situation, Bayes theorem is useful. So let us write down PA denotes the prior probability or a priori probability. The probability of transmitting A, the unconditional probability of transmitting A. A given B, probability of transmitting A given that B has been received, is called the posterior probability or a posteriori probability. And B given A, the probability of receiving B given that A is transmitted, is called the likelihood or the transition probability. Let us now look at the generalized form of Bayes' rule. The generalized form of Bayes' rule. To derive this expression, let us consider a sample space omega, which comprises many events, say A1, A2, A3, A4 and A5. All these AIs are mutually exclusive as well as collectively exhaustive. That means they partition the sample space. Now within the same sample space, let us consider another event, say B, which certainly overlaps with some of the AIs. Now, a typical problem in many applications is that we know B and we need to find out which of the AIs A1, A2, A3, A4, A5 has caused B. For example, if we assume A1, A2, A3, A4, A5 represents 5 different symbols transmitted, that could be transmitted through a communication system, and the received symbol is B. So B may be received because of A1 or A2 or A3 or A4. So the problem is to find out which of the AIs has caused B to be received. That means we want to find out probability of some AI where I is 1, 2, 3, 4 in general up to n, given that B has been received or given B, and as per Bayes' rule, as we just saw, it will be written as probability of B given AI into probability of AI upon probability of B. Now, how to compute the probability of B? As it is clear from the figure that B may result because of A1, it may result because of A2, it may result because of A3, it may result because of A4. In general, it may result because of any AN. So we can recognize these different regions as this is B intersection A1, this region is B intersection A2, this region is B intersection A3, and this region is B intersection A4. That means the event B can be written as the union of four mutually exclusive events B intersection A1 union B intersection A2 union B intersection A3 union B intersection A4, and the probability of B then can be computed as probability of B equal to probability of this whole, but probability of union of mutually exclusive events is sum of their probabilities, the additivity axiom of probability. We can write PB equal to probability of B intersection A1 plus probability of B intersection A2 plus probability of B intersection A3 plus probability of B intersection A4, which is equal to probability of B. The joint probability can be written in terms of the conditional probability as probability of B given A1 into probability of A1 plus probability of B given A2 into probability of A2 plus probability of B given A3 into probability of A3 plus probability of B given A4 into probability of A4. This relation in which we obtain the total probability of B, which may be caused because of A1 or A2 or A3 or A4, is called the total probability. In general, we can write that probability of B in general, probability of B is equal to summation probability of B given Aj into probability of Aj summed over all j in general from 1 to n, and this relation is called termed as the total probability rule. Substituting this expression back into the expression for Bayes rule, we get the more generalized form of the Bayes rule. So we get probability of AI given B is equal to probability of B given AI into probability of AI upon probability of B, which is given as summation over all j from 1 to n probability of B given Aj into probability of Aj, and this is the generalized version of the Bayes rule. This is the generalized version of Bayes rule. Here, let us write down once again. PAIs denote the prior probabilities PAI given B denote a posteriori probabilities. P B given AIs denote the likelihood, and the denominator term is the total probability of B. Bayes rule plays a fundamental role in many practical applications, including digital communications. Indeed, Bayes rule provides a framework to solve a large class of problems, and there is a separate branch of signal processing known as Bayesian signal processing. So we'll look at some applications of Bayes rule in some other modules. So in this module we'll learn what is Bayes rule and what is the total probability theorem. So that's all for this module. Thank you.